Yeah, thanks a lot, both Chaitanya and Mike for the invite. So I'm Jonathan, currently at Johns Hopkins in Baltimore, Maryland. I'll be around for the week, so if anyone wants to meet up or chat or something, happy to do that. And thanks Chaitanya for keeping a cool head with all the technical stuff. So I hope now it's satisfactory for everyone. Okay, so let's get this going with a little introduction. First of all, so this talk is about some approach to doing infinity category theory in a certain synthetic style. So we'll get to what that means in a bit. Just informally, what's an infinity one category, or what's the idea behind those things? So to remind ourselves, a one category consists of objects X, Y, Z, and morphisms, which are like arrows between those objects that we can compose. Depicted like that, should be familiar enough. And so roughly the idea of an infinity category should be that, well, we have a bunch of objects again, X, Y, Z. Also morphisms in the sense as introduced above, but then we also have morphisms between those morphisms called maybe two morphisms or two cells, where the one morphisms would be one cells. So these are like, if we have two parallel arrows, we can look at some way of going from the top arrow to the lower arrow. And we draw this sort of bigger blown up arrow in the middle called alpha. And we can also consider morphisms between those. And that would give rise to like a three morphism. So if we have X and Y here, we have F, G, and some two morphisms, we can look at a even, like a higher dimensional arrow between those. It's this arrow with the three strokes in the middle. And this can continue all the way up. Okay, so.
You can just swipe normally.
Ah, great. Perfect, thanks. Okay, so in our setting, actually what we want, I mean, so, okay, I should say, I kind of have said naively now, what is the point of like infinity categories versus one categories? And there's a way to qualify this dimensionality of morphisms any further. That's what the infinity one means. And so here, so one for infinity one, we want that all morphisms above dimension one, so all n morphisms for n strictly bigger than one are supposed to be invertible. That's what this parameter one means here. And so kind of informally, what it means is that if we have, again, a two cell like this, well, it has a direction a priori, but we want it to be invertible. So we want it to be something like an isomorphism or like a homotopy. So meaning if we can go from F to G, we can also go from G to F. And similarly, if we had a three morphism between two morphisms, that again should be invertible and so on. And what it turns out that this amounts to is something like a one category, but enriched in spaces. So an infinity one category is something like a category enriched in spaces. So from now on, when I say infinity category, I really mean infinity one. And what it means here is that the Hom objects should not be sets as it would be the case for one categories, but they are a kind of space, topological space, more precisely topological space up to homotopy. But intuitively, well, it's supposed to be a kind of space with a non-trivial topology, so not just a set, which would be like a discrete space. And what this implies is that composition now is not given as a strict operation as would be the case for one categories, but it's defined only uniquely up to contractibility and not literally. It's not, I mean, it's not a given structure. It's not a given strict structure as it would be in the case of one categories. So it's only defined uniquely up to contractibility. And what does that mean? So that means using these pictures that we had before, if we have a pair of composable arrows like that, then we can look at the space of composition data, which is now consists of an arrow like this. So it's some composition C of F and G together with a kind of two cell. So together with the filling of this triangle, which is also, it's also a piece of data that we have to make explicit here. And so the space of this data here, so CFG, so it's pairs given by an arrow from X to Z and a witnessing two cell. So the space formed by those pairs, that's supposed to be contractible. So it's supposed to be equivalent to the 1-point space. So an example of such an infinity one category is given by the fundamental infinity groupoid of a topological space. So in fact, that will even be more than just a category. It will be an infinity groupoid. So how is that defined? And again, this is more of a sketch than a definition, but it's supposed to illustrate that it's a natural notion to consider. So it's the fundamental groupoid pi infinity x of a space X. So if we have a space X like this, might have some holes in it or something, a kind of surface. The fundamental infinity groupoid will have as the points, or the zero cells will have the points of the space. The one cells will be paths between those points. Okay, maybe I want to call those paths P and Q or something, and then the two cells will be homotopies, and the three cells will be homotopies between those homotopies, and so on. So that's roughly what this construction looks like. And it's, if you think about this kind of lower dimensional version of it, so compare, for instance, with the fundamental group with respect to a base point, this structure is an improvement of that one-dimensional structure like the fundamental group, because it more naturally, well, first of all, it carries significantly more information because it doesn't just see the loops, but it also sees the higher dimensional homotopies. And it's really natural in that we don't have to do any quotienting, or we don't have to think about parameterization when it comes to composing paths or something. So that means it's also, that's why it also makes sense for it to be a weaker structure, because composition will only be really defined uniquely up to contractibility, but that's good enough for homotopy theory. So that's nice. And moreover, all the higher paths actually will, well, all, I mean, so of course it's gonna be an infinity one category, first of all. So the homotopies are always reversible, but then it's gonna be an infinity groupoid in particular, because also the paths are reversible. And so it's like a groupoidal infinity category theory. So are there questions up to that point? Okay, so what are some problems when talking about these higher structures in that manner? So, okay, maybe I'll have a new slide for that. So problems. Well, to actually set up the theory of infinity categories, you need a lot of one category theory and some fluency in that when it comes to really trying to work with these structures. I mean, just for setting up the definitions to begin with. And this has been done by people such as Jayal, Lurie, and many more. But it's really a very, long-standing matter to give like rigorous definitions and set up a rigorous theory that generalizes the one categorical results and also leads to additional results and additional kind of phenomena that can occur. So it's technically very ambitious. And another thing is that maybe from a more philosophical point of view, infinity categories should be natively homotopical. So they're really not, they're implemented as set-based structures, but they're not thought of those kinds of structures as such. It's rather that the sets come out of the homotopical structures, the way that one should think about them somehow. But in the approaches sort of hinted at above, they're all based on set theory. So the ambient language of set theory is discrete or deals with discrete objects. So is there a way out for this, or is there some alternative approach? I mean, I've called these two items here problems. Maybe they're not so much problems for everyone, but I think they're definitely problems in the sense of being challenges to think about. And that's what some people have done. And there are many approaches that sort of like try to take into account these things that I mentioned. One particular is due to Emily Reel and Mike from 2017. And the idea is to use homotopy type theory, or HOT, to talk about infinity cats. But actually, it's not enough to just use plain HOT for this. In fact, we need some extensions for this, and that's what they came up with in their paper from 2017. And then there's a long-standing program of Emily Reel and Don Verity from, I think, roughly 2013 up until today, so it's still ongoing, under the name of infinity cosmos theory. So that's supposed to provide a sort of unification between different higher categories, so to speak, between different higher category theories, so to speak. And if you combine these two approaches with Mike's major result from 2019, that just plain homotopy theory can be interpreted in every higher topos. So hot can be interpreted, well, more precisely in a certain non-categorical structure. So it can be interpreted in any type theoretic model topos. And you can get such a structure from any infinity one topos in the sense of Grothendieck, Rask, Lorry. Together, I mean, taking sort of together these two research programs by Emily and Mike, and Emily and Dom with Mike's result from 2019, we get this simplicial version of homotopy type theory. So that was initially suggested by Emily and Mike. And it can be interpreted in any infinity one topos of the form simplicial objects in a given infinity one topos. And what that means is that this simplicial hot gives a language to do synthetic internal infinity one category theory. So internal meaning with respect to an arbitrary base infinity topos. So from now on, I guess I'm going to drop the infinity one and just refer to it as infinity. But talking about these foundations, I just wanted to make it sort of clear once and for all. So the work that I'm talking about today takes this idea and generalizes and extends Real Schumann's work on fibrations in that setting, on fibrations of categories. Formulated in the synthetic way. And so it's oriented along Real Verities program to the extent that that seems easily possible, because Real Verities infinity cosmos theory, it's a set-based theory. So a lot of the machinery we can't use internally, but even though, I mean, that being said, it's still it still plays a large role just for finding the right definitions, and then maybe not being able to internally analyze them further, but definitely being able to do so externally, and hence justifying by external set-based sort of model categorical perspectives that the notions that we get are the correct ones. And so this is joint work with Ulrich Buchholz, and some other parts can be found in my PhD thesis from about a year ago. Okay, so before we start with the actual contents, are there any questions up until now? Okay, so let's get started then. What are the notions of synthetic infinity categories that we're considering? So this is Real-Schulman's simplicial type theory. And okay, this is supposed to be an informal introduction into their type theory. That hopefully that it won't be very precise, but hopefully it suffices still to demonstrate how to demonstrate sort of the aesthetics and the kind of feel and vibe that we get when actually working inside it. So in just standard type theory or homotopy type theory in particular, we're dealing with dependent types or type families over a context. But here we also can have another, I mean, we sort of have a way of considering another sort of variables in the context that come from a geometric shape. So I'll get to that in a minute. Just to record, these are gamma, it's the usual type context, and psi denotes kind of shape context. And so what are those shapes? So the idea is that we start with the cubes generated from a direct interval and taking finite powers of those. So we start with 0 cube, just a point, and the 1 cube will be this bipointed direct interval. Then we can look at the product, which gives rise to a square that, well, it doesn't matter too much. I'm drawing it in a maybe kind of a weird orientation. If it confuses you, don't worry about it. Then we also have higher dimensional cubes. So I'm not going to draw in the orientations there. But just be aware that the one faces should be oriented as well, and so on. But then we also allow for considering certain subshapes that essentially will cover the simplices or certain subshapes of those. So what do those look like? So for instance, if you look at the square, well, the 1 cube is also the same as the 1 simplex essentially. But from the 2 cube, which is the square, we can carve out the 2 simplex by taking the upper half along the diagonal. So, okay, all of these shapes should be filled actually. like here. Whoops. Even though we could also consider the hollow versions, I mean, the full shape will have everything filled. So we can carve out, anyway, we can carve out the 2 simplex, for instance, or the tetrahedron. Oops. Okay, maybe I don't want to draw that right now. But there are other shapes that we can also carve out of those simplices, like the pair of 2 composable arrows, or we could consider the boundary of the 2 simplex. Yeah, and then, as I said, like the tetrahedron and the higher simplices. And what's important to note is that those are introduced in a way that they are strict. So they behave like sets in a way. So the arrow, for instance, the 1 cube here, that's really an arrow from 0 to 1. It doesn't involve any homotopy at that point, and that's important to note. So that's important to note because the actual sort of objects of study are the types, and those are supposed to be some kind of space, generalized space, some of which will then be categories in a way that I'm going to explain. So those are definitely going to be homotopical objects, where we have a lot of homotopies present. Yes.
So are the cubes types of the shape context, or like the basic types of the shape context cubes?
So it's a bit, in the way that the theory is set up, it's a bit more complicated. So you actually have a cube layer, and then you have a shape layer, and I would say they're pre-types as opposed to the types. So they will only occur in the contexts. They will only occur at the base.
But like, for example, the triangle in the square is a collection of variables that the square depends on. It's basically that. So yeah, I guess that's one way. I guess that's pretty much the way that it's set up. I mean, the way that these subshapes are defined is by formulas over the variables. And then you have also a reification of, I mean, these are like posets. So you have a reification of the arrows as a relation, as a partial order. Yeah, that's basically how it works. So actually later on, like in the setting that I'm working in, the shapes are going to be coerced to also being types. So every shape gives rise to a type, which is fine in the model, and it just makes certain things easier. But let's not worry about that for now. Are there more questions? Okay, so that's the one feature that standard HOT is augmented by. And then another feature is what's called extension type. So extension types, those go back, I think, initially due to an idea by Peter Lumsden and Mike.
And the idea is to sort of reify the following thing. So suppose we're in a situation where we're given a simplicial type family. So it's a family A over our simplicial type context. So we have we have some type variables and some shape variables. And now we're considering some subshape phi inside psi. And we're considering a partial section of A that is only defined on phi. So it's a term that for every t in phi lands in the fiber A of t. So it's a section. It's almost like a section on like a section of this projection map that we can identify the family with, but it's only defined on the smaller shape. And now we might be interested in all the total sections B that are strict extensions of A. And by that I mean B is supposed to be a section of the projection associated to A, such that when restricted to phi, it coincides judgmentally with A. And this assembles into a new type called the extension type. And that's, so, okay, maybe some word about the notation. So it's written in this notation here where, okay, this part that just indicates, well, it's some element of this type. So it's a total section of the whole family, such that on phi, it coincides with A. And by coincide, I mean being judgmentally equal to A. So externally, you could think of this as just being a pullback like this. So if we have this map shape inclusion here, we can look at the exponential, which is like the restriction map. Then we can look at this single given section A. So I'm just going to pretend to be working over the empty content to make things easier a little bit. And then the extension type, that's just what you get in the pullback here. And if in the model structure that's a fibration, then also the pullback is going to be a fibration. So the extension type will be a fibrant object. So it will be a type. So it's not something that, I mean, okay, so this looks kind of okay, maybe at first glance, but maybe it also doesn't. The point is that we're really working, when we're considering this pullback, we're really working on a strict set theoretic level. So the sections here will be strict sections. And it turns out that this pullback happens to be a homotopy pullback in the right kind of models. So this interpretation will be valid if you set it up correctly, if you set up the semantics correctly. And it's not another important thing to say is that it's this is a new primitive in the type theory. So the way to introduce this is kind of analogously to pi types. Oh, wait.
Technical issue that occurs during every talk.
I see.
We need to wait for the screen to come back.
All right. Yeah, maybe there's time for questions right now.
I guess I have one. so gamma times one of these simplicial thingies, phi or psi, is probably interpreted as the tensor of gamma with the simplicial set phi or psi.
That's right. Yeah, it's an embedding. It's the one that does not make it into an infinity groupoid. So I'm always getting confused about these directions, but it's the one such that the shape becomes just a simplicial space, not necessarily like an infinity groupoid. So not necessarily discrete, but so some of them will be Siegel, but they don't have to be.
You mean phi and psi?
Yeah.
Right. So I'm guessing that phi and psi are just interpreted as bare old simplicial sets. You interpret in some model topos that is maybe enriched over, it should be enriched over simplicial sets, right? Simplicial diagrams in a model topos should be enriched over simplicial sets.
You interpret this as a bisimplicial sense.
Right, but or simplicial diagrams in some model topos, right? So,
yeah, that's one kind of that'll be in the class of models. So in the original paper by Emily and Mike, the setting is even more general than that. Okay. But the models that I'm interested in so far, they all fall under this kind, simplicial diagrams in a type theoretic model topos, which is again a type theoretic model topos, but you have this additional structure that you keep track of these diagrams.
Right. And then over there you can literally see this as some kind of black hole.
Yeah, that's right. Yeah, I've done, I've suppressed the embeddings here because I don't want to really bother with them right now, but it's exactly what's going on. Yeah. All right. Maybe any more questions from the online people? Okay, then maybe I'll go on then. So if we want to be a bit more precise foundationally, it's not enough. So, okay, this is a new primitive and it's like pi types with strict side conditions. And that's also the idea behind coming up with the rules for this type. So you have a lambda abstraction and application, but then you also have these judgmental, these restriction conditions up to judgmental equality in the premise or in the conclusion. And it's not to get a proper theory, it's not enough to just introduce these rules, but turns out we also would like to have an axiom to the real Schulman. It's what's called relative function extensionality. And it basically says that if we have a type in a shape a dependent type in the shape context and all of its fibers are contractible, then all the extension types with respect to any partial section are contractible. And from this you can derive other extensionality principles. And why this is important? It is important because it allows us to compute a lot of stuff with the extension types and to give a lot of equivalent ways of describing types that are about the interaction between the other type formers, sigma and pi, with the extension types and the identity types also. So this axiom accounts for good homotopical behavior of the extension types And in the work of Ulrich and mine, we also want to have this shape coercion. So shapes as types coercion. Which gives us a sort of strictification, destrictification principle that strictification that makes life just a little bit easier. And okay, so now, okay, so this has been kind of abstract and not too precise up to that point, but it's just part of the necessary setup. And in the ensuing discussion, I'm hoping to demonstrate more concretely how these gadgets are being put to work. Before I get to that, are there questions? Okay, so then let's look at some instance of these extension types. So why even bother with this? Well, now we can define. So this is all still a recap of Real-Schulman's simplicial type theory. We can define directed Hom types, directed arrow types from the strict simplices plus extension types in the following way. So if A is the type and xy are terms, we can define Hom xy in A as the type of functions from delta 1 into A that on the boundary, which is just it's just 2 points, which on the boundary restrict to x and y. So the inhabitants of this type will be functions f from delta 1 to A, such that we have strict equalities f0 is x and f1 is y. So it's exactly what it should be. And I often want to abbreviate this here with this notation. So I'm just, so instead of writing Hom every time, I'm writing like arrow from x to y, maybe with the type A as an index here. And this is kind of analogous to the path types in hot, at least the notation, but the introduction, I mean, the way that they are introduced is kind of rather different. But there is going to be some relation in many situations that we're going to get to. So, okay. And it turns out, so using this strictification, destrictification principle, we get an equivalence to the homotopical version of this type, which, well, it's also consists of arrows from delta 1 into A, but now with the endpoints only being witnessed by homotopies and not necessarily judgmental equalities, sorry. And so, I mean, sort of in a dream, you might imagine that, okay, like maybe I can define, I mean, I would like to define this here as exactly what I've written below, but with strict equalities. But that's not something, okay, I'd like to drag this. Is that the drag thing? No, that's not the drag thing.
Yeah, that's a select thing. So you can draw a circle around whatever you want to drag.
Ah, yes. Great. Thanks. I guess, okay.
can erase. Okay, well, whatever. So I mean, this is the sort of object that I want to get. I want to get F together with judgmental equalities at the endpoints, but that's not that's not definable in homotopy type theory because these gadgets here are not types. So that's not the good way to go for here because it doesn't make sense. And so one could instead just use this kind of definition from the get-go. So the inhabitants here would be would not be functions like this with also these two judgments, but it would be triples F, P, Q, and P would be path like this, and Q would be the other path. So it would be paths from X to Y, but only up to homotopy. So it would be, I guess, sorry, that's, so if that's some X prime and Y prime, it would be, the picture would look something like this. So it's not exactly paths from X to Y, but it's sorry, it's not arrows from X to Y, but it's arrows from some perturbed thing at both ends. And in fact, I think Emily and Mike tried with this definition for a little, but then, I mean, it introduces homotopies from the get-go that have to be accounted for in every other construction that uses these hom types. And so I think it became unwieldy pretty quickly. And so hence the idea to resort to strict extension types, just to give some extra strictness. And a nice thing about this sort of scheme to introduce the extension types is that it also, I mean, like primitively, it factors in dependencies. So we can also talk about not just not just functions in a type, but functions into a family or sections. Is there a question? Okay, seems all right. So we can talk about dependent hom types. And these work as follows. So assume we have a type family that I'm drawing as a fibration now. So as a map. So the idea is that starting from a family P over a base B, which is a map from B into the universe equivalently, I can get the projection from the total space, with the total space being the sigma type over the fibers. And I can look at the first projection, which is this pi P here. And then in this picture, I can see that it makes sense if I'm in a situation like this, where I have an arrow in the base, U from B to B prime, and I have points E and E prime lying in the fiber of the respective endpoints of the directed arrow. I might be interested in capturing all the arrows F that get mapped to U, so that lie over U in the family. And this I get as the dependent hom type of the family in the family P over the arrow U from E to E prime, defined as Now the dependent version of the extension type. So it's going to be a section over delta 1 of P of ut that on the boundary restricts the E prime. And in shorthand, I'm writing this as arrows in P lying over U from E to E prime. So this you can compare with the path over or the dependent paths in homotopy type theory. Yeah, and so I mean, just to recall, like delta 1, that's this shape here, an arrow from 0 to 1, coincides with the 2 cube. Sorry, I mean, I guess with the 1 cube written as 2. And so that's the defining shape for the Hom type. And just starting from this, sort of using only dependencies, we can see that pretty quickly this, works well with the vibrational character that we have in homotopy type theory when it comes to converting between maps and type families. So are there questions about this? Okay, I mean, similarly, we can look at other kind of Hom types. I mean, we could look at in a family, we could look at 2 simplices that witness the composite of two arrows. And we can look at like the, I don't know, given arrows lying over that in that configuration, we could look at all the composition data that lies over the composition data below. All these kinds of things we can express using this formalism of extension types. And then again, the nice thing is that, or really like the reason to introduce those from the get-go is that whenever we have an inhabitant F like that, we can conclude, then I know that judgmentally I can rewrite F0 to E and F1 to E prime. Okay, so let's get to the notion of infinity categories in that setting. So let's do the real Schulman. So a type A is Siegel type, or a synthetic pre-infinity category. If the following holds, so if we look at the inclusion from the 2 one-horn into the 2 simplex, which geometrically is the inclusion from the pair of 2 composable arrows into the filled out triangle. So if given, I mean, if when looking at this inclusion, the following map is an equivalence, namely the map that we get when we exponentiate A with this inclusion. So in other words, the restriction map from triangles in A to pairs of composable arrows in A. That's supposed to be an equivalence. And what this means is that the types of triangles like this in A is equivalent to just the type of composable pairs. And of course, we can always restrict from the 2 simplices to this part of the boundary here. But the important thing is that we can come back in an inverse way. And so
intuitively what it means is A has a notion of composition of one arrows, or just arrows, I guess, uniquely up to contractibility. So at the beginning we said that an infinity category in our sense should be something like a category where composition of arrows is defined in such a way that given a pair of composable arrows like this, the witnessing composition data, which is this arrow and the filled thing here, where this space is contractible, and this statement is exactly encoded by saying that this map is a weak equivalence here. So there are some ways to make this more precise, but intuitively, I hope it conveys the idea. That's not, so when I said Siegel type or synthetic pre-infinity category, you might wonder what the pre here indicates. So there is another sort of even better behaved notion of infinity category like structure, which in fact coincides with the right homotopical notion. And that's the notion of RESC type, where we add a completeness condition. So a Siegel type is a RESC type if the following map is an equivalence. So remember, in homotopy type theory, we have these path types. So for all x, y, and a, we have the type of paths in A that go from x to y. But we also can define a type of isomorphisms with respect to these directed Hom types. And that type I'm going to denote x isomorphism to y. And then there's a canonical comparison map called identity to iso. Depends on x and, well, I guess if it's in the pi type, it doesn't depend on, quantifies over all the points. So I have this it to iso map. It's a term of this pi type here. You define it by path induction by mapping the canonical reflexivity term at x to it of x, where it of x is just the constant, the map from the interval into A that just constantly gives x. So since we're looking at a family over a path type, we can define the section by path induction in that canonical way. So this is the canonical comparison between identities in the sense of the intentional identity type and isos in the sense of the directed Hom type, which I haven't really said what these isotypes are, but you can think of them as directed arrows with a left and right inverse, and then homotopies witnessing the left and right inverseness. So that's exactly the definition. And I demand this to being an iso. And so for some people, this might be familiar as the rest completeness condition, which you discover in various contexts. And it's something that makes sense to put in here, makes things a lot easier. And also homotopically covers exactly the right notion, because then types satisfying these conditions are going to exactly be what's called complete Siegel type, or I mean complete Siegel space, or rest space, or object respectively with respect to the given ambient infinity topos. So it turns out that both the Siegel condition that we had here about weak compositions and the rest completeness condition
they can be internalized very nicely and natively in this extended homotopy type theory, and they externally give the right notions. So are there more questions at that time?
Yeah, I mean, you didn't explicitly say it, but doing all of this internally means that being a SQL type is also the same thing as having all fillers for all forms, right?
That's right. Yeah. Well, okay. There's a few things. So externally, it definitely gives the right thing. It depends a bit on what you want to prove internally or not. But it's so definitely doing things. Definitely, if you take this notion here and you externalize it, you're talking about some exponentials here with respect to this co-tensored. I mean, the shapes being co-tensored over the whole model structure, and that unwinds to exactly the external Siegel condition. Yeah, some of these things I would say it's not so clear, like to what extent you can prove them also internally, but externally certainly. So we know that this is the right notion. I mean, this has been done by real Schulman using some results from Joyal or Joyal-Tierney, I think. Yeah, but and the same for the rest condition. Oops. Yeah, and the same for the rest condition actually. So so the rest condition here, right? It's not it's not formulated as an I mean, so this you can write as an orthogonality condition, and then there's some nice things going back and forth between like pull by columns or like orthogonal liftings in diagram that you can do using these things that we know about extension types, using strictification, destrictification. The way that the rest condition is formulated here, it's not in that style. But if you coerce the shapes to be types like Ulrich and I usually consider, you can define the free bi-invertible arrow as a co-limit, certain co-limit over the simplices. And then, so this you can find a discussion externally about this in the real Schulman paper. But you can, if you internalize if you fibrantly coerce the shapes, then this you can also do internally, meaning that you can show that this condition is in fact equivalent to the types being equivalent to either endpoint inclusion into the free bi-invertible arrow or the terminal projection from the bi-invertible arrow. So it ties in neatly with these homotopical algebra considerations. And so then there's a third notion that had been introduced. So a type is discrete or a synthetic infinity groupoid. So let me just go back. Did I call? So here, I mean, a Siegel. I said I defined what a RESC type is, and these are exactly the synthetic infinity categories. I should say this. And then a type is discrete or a synthetic infinity groupoid if the following map is a weak equivalence. So before we had looked at this, before we had looked at, so I guess I can draw the circle. No. Before we had looked at this comparison map of identities to isos, but by post-composition, we also get a map from identities just to arrows. So it goes from paths to just directed arrows and demanding that that be an equivalence. gives the notion of synthetic infinity groupoid. And from this, you can actually prove that it's also Siegel and rest complete. So you don't even need to impose this assumption here. Okay, so some important consequences are, well, Siegel types really have a sort of categorical structure, or flat categorical structure, if you want to be more precise. So they certainly have composition of morphisms. They have identities. And the corresponding laws up to homotopy, so witnessed by proposition by propositional equalities. Any function between Siegel types preserves composition of identity up to paths again, up to propositional equality. So any function between Siegel types happens to be an infinity functor automatically, which is nice. So a lot of properties such as functoriality or naturality that usually are kind of, well, not automatic, to say the least, and maybe sometimes, especially in the higher setting, are hard to prove. They will very often come out to be sort of satisfied for free in this setting because of principles like this. And then one can also show, so that's still a recap of real Schulman's work. All of these results, if A is Siegel, then all the Hom types are discrete. So I didn't say this, but in this picture, these are the spaces. The synthetic infinity groupoid are the spaces. And so, I mean, the types are not the spaces, but they're the simplicial types or the simplicial spaces. And then some of those are infinity categories and some of those are spaces. And so this remark or this proposition tells us that, yes, we can see synthetic infinity categories in that sense also as categories enriched in spaces. And a type is discrete if and only if it's discrete if and only if all arrows happens to be isos in the sense of the directed iso. Yeah, and okay, I mean, there's something else I should also say again. The Siegel condition, like here, as well as the rest condition, like here, they're really conditions, so they're propositions in the homotopy theoretic sense. So being Siegel or rest, it's not additional structure. It's a proposition, which is nice, and also a bit strange because now being a category, I mean, now, usually we think of a category as a structure on something, but now being a category is a proposition. So it's strange from some intuition, but it's exactly the right thing coming from a different intuition, I guess. And then similarly, being discrete is also a proposition because being an equivalence is a proposition. And we even, so in this theory, we even get, we don't just get functors and categories, but we also get natural transformations. So natural transformations, they're defined to be members of Homs between arrows or functors between two, let's say two Siegel types or two REST types, which maybe we can write like this, the type of all of those. And one can show that just from this definition, we get induced naturality squares. So any arrow u from A to A prime in A gives rise to a naturality square given a sigma like that. And an arrow u gives rise to a naturality square. Just as we would like. Actually commutes, so that's good. Okay, other questions at that point? Okay, so let's get to the point where we're talking about vibrations of those things. So vibrations of synthetic infinity categories. So what's the idea? So any dependent type we can naturally see as a family or map into the universe, but we want functorial families. So I'll get to what that means more precisely, but basically we want something that for not just, okay, for any point we want to get a type in the universe, but actually for any, if the base happens to be Siegel or RESC ideally, we would also like to get an arrow between the fibers for any arrow in the base. And that all should work out nicely. And the idea is that, well, that's obvious. I mean, that's not going to be for free. It just won't be. But so it'll be a condition on the family, and that should correspond to a condition on the associated total type projection. So it should give rise to a notion of vibration. And of special interest are the co-Cartesian vibrations. So what are those like? We first need the notion of co-Cartesian arrows for that. So from now on, I'll always assume that we're looking at a family over a RESC type B. And all fibers PB will be RESC2. And okay, then I can look at the associated projection like this. And I'm going to assume I have an arrow U from B to B prime. And I have an arrow lying over called F from E to E prime. And F is going to be called co-Cartesian over U if it satisfies the following properties. So for every arrow that I can post-compose U with, so for every V from B prime to some B double prime, I can look at the composite because I'm in a RESC type. So for all V and for all H lying over the composite with domain E and codomain some E double prime lying over B double prime. So for every V like this and for every H like this, I want a unique filler here. So uniquely up to homotopy. I want some G here. And this I can phrase as a condition in terms of pi and sigma. So formulating that an arrow in the family P over an arrow U, called the arrow F, is co-Cartesian, amounts to saying, okay, well, for all V like that, and for all H, I'm just being sloppy here to save time. There exists some, like the type of G such that GF composes to H, that's supposed to be contractible, which corresponds to the demanded uniqueness of the filler. So that internalizes the known notion of co-Cartesian arrow, and it can be expressed in various ways, as you might be more familiar with from quasi-category theory or complete sequence space theory. So all of this we can do, or even infinity cosmos theory, actually. And this gives rise to a notion of co-Cartesian family or co-Cartesian fibration. Which is a family P over Resk type B, such that, well, all the fibers are Resk again. So it's this assumption that I've written here that I'm not going to copy, such that for all U for all arrows U in the base with a point in the fiber over the domain, the type of, I mean, there exists a co-Cartesian lift. So some F from E to some E prime over U in P, and I'm going to decorate this co-Cartesian lift with these 3 arrows here that go into the forward direction. Okay, and so this definition is also well behaved because being a co-Cartesian lift is determined uniquely, essentially in a unique way. So this condition also turns out to be a proposition. Right. So I mean, geometrically, what it means is if we have E and B here, the associated projection to the family, we have the U here, B to B prime, and we're given E on the left side here, then there exists a map uniquely up to homotopy with respect to this fixed thing, E, that happens to be co-Cartesian and lies over U in the sense of the dependent Hom. Okay, other questions? Okay, so it turns out this definition is really well behaved. So it yields the desired functoriality. So we get for each arrow, we get a map, like a transport map from one fiber to the other fiber in the covariant direction of the arrow. And what it gives is the endpoint of the co-Cartesian lift. So for any, well, I mean, the map, how it works is if we have our U and we have E in the fiber, gives us the endpoint here of A. That's determined uniquely up to
a path in the fiber. And this transport composes in the right way. And lifts of co-Cartesian lifts of isomorphisms or identities which over rest type coincide. So we can always assume an identity to be, to assume an isomorphism to be a reflexivity or the it morphism. Right, so lifting co-Cartesian lifts of identities are always identities. And then we recover a certain characterization of co-Cartesian families in the following way. So this is due to Ulrich Buchholz and myself after results of real verity in the infinity cosmos setting. So let's assume P from B to U is a family with B and all PB resc. Then P is a co-Cartesian family. If either of the following condition holds. So first condition says that it's called the Chevalier criterion. And it starts as follows: consider the left endpoint inclusion of the point into the interval. This gives rise, so if we take the vibration that corresponds to the family pi p from E to B, we exponentiate it by this inclusion. We get a square like that, where we have the domain projection here in the base and the domain projection in the total type as well. And we have a comparison map to the pullback, which I'm going to write as the comma object, pi comma b here. So this I call R, and the condition is that if I consider R here to the pullback, then this is supposed to have a left adjoint right inverse called chi, left adjoint right inverse. So that means chi is the left adjoint of R in a certain sense, such that the unit of this adjunction is invertible, or an iso or homotopy. And the idea is that this chi here acts as the lifting map. So to any UE, where UE is a pair like this, U with the point E over the domain, it assigns exactly the co-Cartesian lift. So I'm going to call this P shriek of U with respect to E. It's sort of the canonical name I'm giving. And okay, yeah, we can prove this internally. And there's another criterion. Maybe I'm not gonna talk about this right now. There's another criterion where you don't get the notion via, maybe I should go back with the slide. You don't get the notion via this lifting map, but you get it via transport map. So instead of assigning to this data the whole arrow like this, you only assign you assign to this data only the endpoint here, but still you do it in such a way using a fibered adjunction that it gives you, it's gonna end up giving you the right thing. This criterion is very important because it implies a lot of the closure properties of these fibrations that that we care about. For instance, stability under pullback or stability under taking sections, or just composition. Okay, so let me just mention there also exists like a fibered left adjoint criterion, and criterion. And in this whole story that uses coherent adjunctions in as hot due to real Schulman, and also real Verdi, where real Verdi looked at this in the context of infinity cosmoses and showed that just strict two categorical adjunctions give uniquely rise to a fully coherent, simplicity coherent adjunction. And this, as a result, is kind of used to justify and I think also motivate or justify part of the definitions of, or part of the different but equivalent ways of defining and presenting coherent adjunctions in real Schulman's theory. Then we augmented this by also having left adjoint or right adjoint, right inverse adjunctions and fibered adjunctions, but it all relied on, on the real Schulman's definition just for coherent adjunctions in this theory to begin with. And so there are a lot of consequences of these characterizations. So closure properties. We also get Cartesian fibrations just in a nice way, just by dualization in an appropriate sense. And specialized to or generalized from the discrete case. So that's a real Schulman's covariant, discrete covariant fibrations, which are like synthetic left fibrations that are special cases. So there you would ask for this comparison here to be an equivalence and not just a left adjoint, right inverse adjunction. And we get many famous, I mean, many known examples. Such as comma fibrations, and hence in particular the codomain op vibration, I guess I want to call it. Well, also comma op vibrations, I guess. So those are all co-Cartesian fibrations or co-Cartesian families. We get that the domain map is a fibration if and only if, sorry, it's a co-Cartesian fibration if and only if
the base has pushouts. So that you can find in our work. More generally, so there's a theory of limits and co-limits by now by Bardomiano Martinez. In the simplicial type theory, and also a treatise in the master's thesis of Backe. Okay, so other questions up to that point? And I should mention we also get the free co-Cartesian up vibration, which, if you start with the vibration, gives you something that's known as the family vibration that also has some interesting properties, some of which I'm discussing in my thesis. But yeah, we definitely can perform this construction and prove that it's an up vibration. And we can, I mean, we have a sort of baby version of the statement of monadicity there, but not an overall theory about that in a way that would be, that you would like to have it, but okay. That has to do, that somehow has more general reasons having to do with how the type theory is set up. So if there are no questions right here, I would go to a nice application of this notion, namely the Yoneda lemma. For these kinds of vibrations. So this you can find again in our joint paper, and it generalizes the discrete case from real Schulman and internalizes, oops, what am I doing? And it generalizes real verities analogous Yoneda lemma formulated internally to infinity cosmoses. So what's the idea? So let's say we have co-Cartesian vibration, again over a Resk type. And we have a term B and B. Well, okay, I should say this notion of co-Cartesian vibration gives rise to a notion of co-Cartesian functor. So that's a fibered functor that preserves fibered functor between co-Cartesian vibrations that preserves co-Cartesian arrows. And the Yoneda lemma vibrationally can be seen as the following statement. So look at the fibered functor from, so I'm doing the covariant case. So look at co-Cartesian functors from a sort of representable, covariantly representable vibration with respect to B. So it's the codomain projection of this comma object here, which as the fiber, it's a Homs in B starting from little b. And look at the co-Cartesian functors into a vibration pi. Covariant, I mean a co-Cartesian vibration. And you want to classify those as just the elements of the fiber at B. And so there is certainly one canonical map going from left to right, which is given by evaluation at the identity of B.
What's capital P? Sorry.
That's the family. So yeah, so
yeah. Got it. Just to clarify.
Mm-hmm. Yeah, so the family, I mean, to be explicit, like
From B to, yeah.
Exactly. So that corresponds to pi, and I'm just dropping the P that corresponds to this thing, map from E to B. Okay, so well, okay, but what are those? So okay, whoops. So we can look at this type of co-Cartesian functors here. And well, at first glance, it's just a sigma type that we can try to define. And well, okay, it'll be a nice sigma type just using propositions, because co-Cartesianness of a functor can be phrased propositionally. But this we can also write equivalently as the type of sections from the comma object to the reindexing of P along the codomain map. But we want to take the co-Cartesian, so that's again going to be a co-Cartesian family, and we're looking at co-Cartesian sections. And by co-Cartesian sections, I mean sections of this family such that the action on arrows here gives co-Cartesian arrows in the family. So since this actually happens to be a discrete vibration, all the arrows here are co-Cartesian. So the condition is to map any arrow to a co-Cartesian arrow right here, which means that seen as a section over the pulled back family, it has the section has to be co-Cartesian. Okay, so, and if we view it in that way, there's actually a nice way to understand this as the directed arrow induction principle. Maybe I should write that out. Oops. Yeah, okay. Directed arrow induction principle so it leads to a dependent Ioannida lemma, which in the original form you can find in real Schulman, and later in the cosmological form in real Verity, and then in this kind of synthetic type theoretic form, not in the discrete but the co-Cartesian case in our work. So I'd like to say something about the proof a little bit. So proof strategy of this is as follows. Essentially, it's going to be just a corollary. Okay, I shouldn't say just, but that's what it will be. So it will be a corollary of this following results, also analogous to the strategy that is used in real Verity. Let's say we have a RESC type with an initial element. Initial element B in B, meaning that for all x in B, the type of directed arrows from B to X is supposed to be contractible. then the following map is an equivalence. So we can look at the space of the type of co-Cartesian sections into the fiber. Well, and how do we get a map? Well, but just by evaluation at the identity. No, by the evaluation at the term B, or the element B. So that will, I mean, given a section, that will give us, of course, an element in the fiber. And I'm claiming that this is supposed to be an equivalence. And I mean, a posteriori, that also shows that that this type of objects here actually happens to be a rest type too, because then it's going to be equivalent to a rest type. Okay, how can we show this? So first we have to construct an inverse, and after real varieties, suggestively, I'm going to call this little y for Uneda. Okay, so how could I define this map? So, okay, what I first have is I start with B and then some element D in the fiber over B. And now I want to produce a section out of that. So assuming I have a point X, I want to get something here over X, because I want to define a section, and maybe I have to use this point D here somehow. But this I can do because I have the initial inclusion here. So I call this empty set X for the inclusion of the initial element into some given point X. But then I'm also in a co-Cartesian fibration, so I get this co-Cartesian lifting. I get this co-Cartesian lifting here. So the map Uneda of D of X, I just define it to be co-Cartesian transport over the map empty set X of the point D. Okay, that's the definition. So I now have to show that it lands in co-Cartesian sections. In fact, otherwise the theorem would not be true in general. I mean, it is actually true that when I look at this Uneda map just in the sections without the co-Cartesianness condition, it gives a left adjoint right inverse of this map, but it only descends to an equivalence when I restrict to the co-Cartesian sections. So I have to show that this yields a co-Cartesian section. So second is co-Cartesianness. Well, I mean, it's still part of the construction actually, right? Otherwise it wouldn't be well typed. So, but let's still do it like that. So show co-Cartesianness. Okay, how do I do that? Well, I have to show that for all u from A to A prime in B, the action of y, so yu, sorry, I have to show that for all those arrows and for all D in the fiber, the action Uneda du from Uneda dA to Uneda dA prime is a co-Cartesian arrow. That's what it means for the section to be co-Cartesian. the action on any arrow ends up being a co-Cartesian arrow. So we want to show this. And how do we do that? So the action of the arrow, you can view it as arising from a naturality square from the following. So we define a natural transformation in the between not sections, but just functors from B to E, from the constant functor with value D to YD. And how do we define such a thing? Well, it's a natural transformation, and it ends up being by using interactions between the extension types and the pi types. It ends up being a family of arrows like that. And we define it as follows. So equivalently, it suffices to give for any x an arrow from D to Y dx, but we define it simply to be the co-Cartesian lift over empty set x with respect to D. So that was by definition exactly the transport over empty set x of D. And so the naturality of square of this, it look as follows. So if we look at this square in the base here, right. It turns out that above we get naturality square connecting the constant map with the action of YD on U over the given U here, where these horizontal arrows are exactly the naturality maps at x and x squared, but those are co-Cartesian. And then by cancellation of co-Cartesian arrows, we get that YDU also has to be a co-Cartesian arrow. So I haven't really said much about the formal properties of the co-Cartesian arrows, but it turns out they satisfy the formal properties that we like: closure under composition and the correct cancellation law. So finally, we also have to show quasi-inverseness. Oops. Or like inverseness of this Y arrow to evaluation. So in the interest of time, I don't think I'm going to do that, but it's also it also uses like a similar idea, using a natural transformation defined kind of in a similar fashion. And well, a version of this you can also again find in real verities infinity cosmos theory. But what's very neat about this here is that you don't really don't need to show any naturality, or just compare this with the one-dimensional Yoneda lemma, because here these type of naturality arguments just come out of really defining natural transformations in that way, inhabitants of a Hom type that you can rewrite a little bit using pi types, and then it's just, you know, giving this map here, and you don't have to show, you can use the naturality from what you've proven before, but you don't have to show it. And I think that's quite neat. So yeah, if you want to read up on this, you can look at Ulrich's and my paper from 21. And I mean, so to sum up, we get the dependent Yoneda lemma from that. So if we have a co-Cartesian family Q depending on this arrow type here, then and B again should be a rest type, then evaluation from the co-Cartesian sections into the fiber at the identity should be an equivalence. And it's a corollary of the previous proposition, because the identity is initial in the co-slice. And if you compare this with path induction, or based path induction in that case, then you can see it really generalizes in a strict sense, because we're in rest complete setting. Generalizes, you know, in a strict sense, this this sort of the original path induction principle, because I guess I should add B here, because this looks like you have a type family from, yeah, I guess paths from B to B prime. So you have a family over a base path space. And then the idea is that the sections of this, so B prime together with a path into P, B prime P, are equivalent to just the sections at the identity. And this holds true for any type family in plane hot or at the simplicial type level, because any type family is like an isofibration with respect to those paths here. But then if you want to refine this to like a directed kind of path notion, like the Homs here, well, that's kind of, well, that's what you need. You need an additional, you need the co-Cartesianness, and you need co-Cartesian sections, but then it kind of works also similarly with these Yoneda style arguments. So I guess I should conclude the talk now, so that we have like, I guess, 5 minutes for questions and discussion. So let me just say some further work. So my conclusion, so what you can find in my thesis is two-sided versions of this, two-sided versions where you have vibrations that have like both, that have some co-Cartesian and some Cartesian dependency over different types. So again, should compare this with real verity. Then I have a chapter and article about vibrations with internal sums in this setting, or dependent fibered sums, I guess, which takes some work by Benabou, Streicher, Moons, Giblatze, Frey, and treats it in the setting. And then I'm also considering, then there's just like a semantic consideration about these extension types that has to do with strictification and like how to like strictify these type formers so that we can get an interpretation function in the appropriate sense of logic. So strict type formers. Yeah, and then there's additional work in progress with Ulrich together that have to do with universes, universal vibrations, and maybe opposite and core types. So these are all gadgets that you would like to have if you wanted to do higher category theory parallel many developments from like higher category theory in different models, and these give rise to like even more extended versions of this type theory, but I think they're interesting to consider. So thanks a lot for everyone's time.
So open for questions. And maybe I'll try the, okay, no, good. I guess maybe I have one question, it's kind of naive. It doesn't seem like you use anything more than 2 or maybe 3 truncated simplicial objects.
Well, yes and no, but go ahead with your question first.
What if you took, I don't know, simplicial type theory, but where the simplicial bit ends at dimension 2 or 3?
Right. Okay. So, all of this is untruncated. Everything that I've said, at least, it's untruncated.
Mm-hmm.
But it turns out that for all of these developments, you actually don't really have to look much, if at all, beyond dimension 2. So you maybe for some foundational things like the elementary properties of these Siegel types that Mike and Emily have proven. I guess there maybe you need to go to dimension 3 at some point, but very often you can, you just look at the 2-1 Horn inclusion into the 2 simplex or something like that. So yeah, it's it ends often that you sort of can make do with these lower dimensional arguments. I guess this is partly owed to the fact that you work with these internal exponentials. So you look at the whole space of 2 simplices in a type, or the whole rest type of 2 simplices in a type, in a rest type or something like that. So you're always carrying around more stuff than you need to be explicit about, which I think is nice. But yeah, you don't have to. Yeah, it's just you have more stuff present, but somehow for a lot of the things you don't need to use more stuff. But I think if you really were trying to prove something like the Siegel condition uniformly for all dimensions, that could again be
a bit hard, I guess. So I think Emily and Mike have looked at this briefly. Ulrich and I also thought about this a little bit, and it's not, I mean, yeah, it wasn't so conclusive for us. So it could be that something like this, where you would have to uniformly quantify, you know, internally over simplicial dimension, yeah, maybe you can't really do that, or we don't know because we don't know about, you know, semi-simplicial types and plain hot or something like that. So maybe some of these things you can more easily at first glance only prove them on the level of, like, you know, the course of, you know, a to the delta n instead of a to the delta n itself or something like that. So I know that there's some definitions in the real Schulman paper that go over all simplicial dimensions. For instance, I think the definition of the boundary or something like that. And I mean, if you allow that, this external quantification, I mean, I think it's fine. But then if you wanted to do this in a proof assistant, you know, then maybe you would have to think again a little bit harder. And speaking of which, I should also mention there is a prototype proof assistant that you can try out online. It's called RZK for RESC, I think, by Nikolai Kodasov. You can find it on GitHub, where some of the stuff involving like computation with extension types, you can formalize it a little bit in there. And yeah, but I mean, yeah, I hope this answers your question somewhat.
Yes,
Yeah,
and I think Mike had a comment.
This is kind of the whole point. What you, Chaitanya, what you were saying is kind of the whole point to me, that infinity category theory is supposed to be just like one category theory for the most part. And so, like, the fact that we can develop it without referring explicitly to all the higher dimensions is really the goal. So it's really great that it seems to work out that way.
Right, exactly. That's what I would have thought as well. And I think that it's really quite magnificent that you said. That was for me, you know, the point at which I was basically convinced about this simplicial hot stuff.
Agreed. Yeah, it's yeah, I think it's nice from this perspective, and I mean, especially dealing with this whole vibrational stuff, I found it I found it a good mix of languages in a way, because like sometimes because that's where, I mean, mixing categorical constructions and arguments together with more type theoretic ways of doing things. So you still can do the vibrant replacement of maps. You can always view them as a total space projection coming from some family, just as in plain hot. And this, yeah, I think that, you know, you can use this whenever it's convenient, but then you can also, you know, like, you know, that works well with the categorical constructions, and you can use that whenever it's convenient. So yeah, that has been proven very useful, like when whenever I've been working with that.
I guess the next thing to define would be symmetric monoidal infinity.
Great. Yeah. So yeah, no, exactly. So yeah, it's yeah, I would love to be able to do that, because you, like, due to Luri and other people, we have a nice way of doing that in terms of vibrations, but that's where this issue comes in. Like, your base needs to be a certain kind of thing that should be a RESC type, and defining these RESC types, even for categories of not so complicated shape, yeah, it's kind of it's kind of not so easy or not so clear what's a good way if you don't want to throw in a bunch of axioms. And so that's why. So I would love to have some, actual higher algebra in this kind of theory going on, especially because you can mix it with all kinds of things. So you could add differential cohesion. So there's very exciting work about the meta theory, both of these sort of like generic multimodal type theories where you get like opposite arrow types or twisted arrow types by reindexing, by like pulling back along endomorphisms of the base simplex or whatever category, and then you can ask for those to interact well with differential cohesion. So there's like good work about these frameworks that I think solidify the theories, to make them really workable. But like this big issue that still kind of is around is like a good treatment of universes that goes through like smoothly without imposing too many axioms. Because otherwise there's just not many RESC types that you can actually look at. So.
Have you built the RESC type of finite sets?
No, we've thought about this a little bit, but yeah, it's not definite, or it's not done. So yeah, that's kind of yeah, you can, if you look at, you could maybe look at a version of directed hits in that setting and try to go from there. But yeah, I don't have a definite picture about that. But yeah, that's, all these kinds of things are exactly what you would need for symmetric monoidal infinity cats or infinity operats. And yeah, and it would be nice to invoke the universes, the universal co-Cartesian vibration and the things derived from that. And then I think you could really get going. And there is some work that outlines the path, but yeah, still thinking about it so far.
I guess one thing that might be doable without like infinity operas or anything like that is presentable infinity categories. So you can talk about maybe, then again, you have to talk about things like pullback bonds, arrow infinity categories.
Yeah, well, this we can do. Especially this is kind of very nice in that theory. But even, without having any kind of RESC universe, it's hard. I guess in some sense you could do like abstract localization theory. We have a good theory of adjoints, I think. So there are some things that you could do, I think. But well, and we can talk about presheaves, but only seen as vibrations, not in the right kind of indexed way. We can do them also in some indexed way, but again, we won't see that they factor through the right universe, and so it's the same issue again.
If there are no more questions, thanks again, Jonathan, for a great talk.